vais juste me chercher un petit verre d'eau, je reviens.
Ok, ben merci beaucoup Aurélien pour intervenir ce matin. Tu es chercheur Inria. Moi je t'ai croisé indirectement parce que tu es intervenu dans une conférence qui se tenait à Vannes.
Ouais.
Et où tu as parlé d'apprentissage fédéré, et ce sujet me semblait intéressant pour qu'on en discute au sein de l'équipe, et donc voilà pourquoi j'ai sollicité ton intervention ce matin. On va passer en anglais,
Ouais.
parce qu'on a des noms francophones chez nous, et je vais te laisser nous présenter ton travail avec un focus sur des problèmes de vie privée.
Ouais. Okay,
Merci.
thanks a lot. Thanks a lot, Laurent, for the invitation. Yes, I'm a researcher at Inria, based in Lille, in a team called Magnet. So we do machine learning in this team, and with a big focus, in particular on my part, on privacy preserving and federated and decentralized machine learning. So this is going to be the focus of the talk. Indeed, I have reused maybe some content from this presentation that I did at CAP, which is like the French conference in machine learning. But talking to Laurent, so I have modified a bit the second part to focus maybe on kind of privacy aspects, because he said that was maybe of particular interest to you guys. So here's a little bit of the outline. So I will start. So it's maybe not very easy for me to, I don't know a lot about maybe the background of the audience, to be honest. So anyway, I will start with a more kind of introductory part on federated learning, to start by kind of motivating federated learning, why it is interesting, and introducing kind of like a first, let's say, standard baseline federated learning algorithm. And then I will switch to kind of a little bit more focus on privacy aspects, how to guarantee formally that by doing federated learning, so by learning models over the data of different participants, the participants can make sure that the others don't learn too much about their own individual data. And so there will be two parts. So I will introduce a little bit first the notions around differential privacy, which maybe some of you already know, but I think it's probably not very safe to assume that everybody is very familiar with differential privacy. So there will be also a bit of introduction to that. And then we will see how to apply this, to use this idea of differential privacy, which is a formal way of measuring how much algorithms leak about their data. How to use that to make sure that the federated learning algorithms are privacy preserving. And I will kind of discuss about two settings, but I will get back to that. Okay, so please feel free to interrupt me. I think it's much better to make this interactive. So if there is anything not clear, feel free to ask me.
Okay.
All right. So the starting point maybe for federated learning is to think of it as a shift of paradigm. So the standard setting in machine learning typically considers like a centralized data set, right? So we have some data, and we have access to it. Maybe in the simplest case, it sits on the machine that we are working with, say the laptop, and we want to train a model on this data. More generally, by centralized, I will also include the cases where maybe the data is very big, so it's not maybe on a laptop, maybe it's on some cloud or data center or cluster of machines. So maybe not necessarily sitting on a single machine, but it is in a system that is tightly coupled, and access to data is efficient. There's no specific restrictions to access the data and so on. Okay, so this is the standard setup, right? You want to train on data that you can easily access from a unique place. Of course, the problem with that is that in the real world, this is not really how data is, at least in many applications. Originally, the data is actually decentralized. So it doesn't sit on some cloud, but it's collected by different parties, right? So you can think of medical data, which typically is located in different medical institutions, like medical hospitals, who each store data about their patients. You can think of different companies, like client data from different companies, things related to connected objects, like of course smartphones. So each of our smartphones stores kind of some data about the usage that we make of the phone. Things about connected cars, obviously, which also kind of generate their own data from the sensors and from the driving of that car. And everything also related to sensors. Okay, so in all these cases, data, doesn't appear in the cloud, but it's really decentralized across different parties. In some cases, across a very large number of parties, right? And so there is a dichotomy here between the standard setting of machine learning, which assumes centralized data, and where data really is in practice. So how this is typically solved, or most often solved, is by centralizing the data, right? So what you can do, or what you could do, is instruct all these different entities to send their data to a server, big server that will store everything, and then you would do the learning or the data analysis there. Okay. The problem is that we don't always want to centralize data. And there might be two big reasons maybe for it. The first one is maybe sending this data is very costly, either because it is large. So if you think about self-driving cars, so people expect that a single car will generate like terabytes of data each day. Okay, so it might not be so convenient, and in any case, it would be very costly to transmit this data for like billions or millions or billions of cars all the time to some gigantic server. And there are cases where data is not that costly, but maybe transmitting data or communicating in general is slow or costly. And so this includes typically wireless devices, which have kind of limited bandwidth, limited power, and so it's costly to communicate, and so you should avoid to send a lot or frequently some data over the network. So this is the one first reason. The second reason that we're going to be most concerned about in the context of this talk is when data, we don't want centralized data because it's considered to be too sensitive to be centralized. So this includes personal data. So there is kind of growing public awareness and also increasing regulations on when we can and how we can collect such personal data and process personal data. And so we see also in different fields, maybe users or some users at least pushing for kind of more privacy preserving solutions where maybe their data is not collected and sent to some server and processed in a way that they don't understand, but they want to kind of keep maybe their data, their personal data under their control. And there are also other cases where maybe data can be sensitive or too sensitive to be shared. So typically cases where keeping control of data gives a competitive advantage. So of course there are cases in business. We've seen recent examples of, for example, in the pharmaceutical company sector, where different companies are kind of willing to collaborate to maybe achieve a common goal, which is like speed up the discovery of new drugs. They are willing to collaborate for that, but they are not willing to share their data because they have secrets, trade secrets, and that they don't want to know that the other pharma companies know which molecule they are currently working on specifically and so on, right? So in a way, because it gives them a competitive advantage to keep this information from competitors. This happens also in research, in particular in medical research, where kind of people spend a lot of time collecting, curating data. And this gives them a competitive advantage for publication, right? And so they are not always very willing to just give away this data, although they are often interested in maybe collaborating with other institutions that also have similar data, so they can have maybe more powerful studies and so on, okay? But in this case, they are not very willing to share that data and to centralize it. So this is about centralizing data. Okay, so there are cases where we don't want to centralize data or we can't centralize data. Then there is another extreme approach maybe to solve this dilemma, right? Which is we forget about collaboration and we just let each person, each entity to learn on its own, right? So of course this has other issues related to the fact that the local data on each participant may be very small. So you, in terms of machine learning, you can get a poor predictive performance, maybe like things like overfitting, right? Or in cases where you train models not so much for their predictive performance on unseen data, but more as a way to draw conclusions about a phenomenon, which is often the case in medical studies, then you might get non-statistically significant results, right? So you don't have enough data, so you cannot conclude reliably on the phenomenon you're studying. And then there is another type of problem that can happen is that the local data might be biased in the sense that it might not be very representative of the target distribution or the target population that the study, for example, is aiming at. So again, for medical studies, for instance, if you think about different hospitals, they each have different patient population. They also have different care habits. And so something that you learn maybe on the data on one hospital might not, transfer very well or apply very well to the whole population or to the population of another hospital. Okay, so there are these two extremes and they are not very satisfying. And so federated learning is really about trying to get the best of both worlds, right? So put kind of in an informal way, federated learning aims at being able to collaboratively train machine learning models across different entities that hold data while keeping this data decentralized. So while essentially keeping the data where it's collected or, in the locations where it belongs originally. Okay, so one way I like to put it also is maybe it's a way to go from sharing the data itself to sharing the usage of data. Okay, so in federated learning, you don't share the data, but you agree on some common goal, like train some machine learning model, and you want to achieve this goal without directly sharing the data by sharing other kind of quantities that will be more aggregated and sufficient, essentially, to achieve the objective. So federated learning is a very booming topic. So the term was coined in 2016. Of course, it's related. I mean, there was research before 2016 that kind of was related to this, but it really when kind of the topic picked up. So I started working on federated learning around that time, like 2015, 2016. And nowadays there are thousands of papers each year on that. So of course, not all of these papers are good or so interesting, but definitely there is a lot of interest, which is fueled by kind of these privacy, kind of higher privacy expectations and kind of more strict regulations, and also, yes, the kind of barriers to analyzing data in some specific fields like the medical domain. And so we have seen a lot of research. We have seen also a lot, not a lot, but at least some first real-world deployments by companies and also researchers. So Google notably deployed some federated learning on the next word prediction task. So kind of predicting, on the Gboard, so the Android keyboard kind of for prediction of what you're going to type next. So essentially doing this without, getting the text data from their users, which is obviously quite sensitive data. And also deployments, for example, in the medical domain. So I'm actually involved in a collaboration with some university hospitals in France on kind of using federated learning for multicentric medical studies. It is also very multidisciplinary, as you can expect. So of course there is, probably machine learning is at the center of it, but there are also many interesting questions related to optimization, statistics, of course, privacy and security, also networks, systems, and so on, right? So there's also kind of a lot of work on and around federated learning in these different communities. which makes it sometimes not so easy at the moment to keep track of the progresses and so on, because there is a lot of research and also happens in different fields. So I'm going to try to kind of give you a little bit of overview of how federated learning works now. And maybe before I start digging into maybe a concrete algorithm, let me try to summarize maybe a few key differences with what sometimes is referred to as distributed learning, which you might have thought of. So the idea that I want to do machine learning but distribute the computation across different machines, right? Which is of course quite an old idea, right? And there has been a lot of work prior this idea of federated learning on that, but there are, in my opinion, quite a few significant differences that make federated learning kind of a separate and a specific topic of study. So just to clarify what I mean by distributed learning is the case where data is centrally stored. So you actually have access to the entire data. Maybe it's stored in some kind of data center or something. But essentially this data is large and you want to train faster than just training the model on a single machine. And so what you do is that you distribute data across different machines, different workers that can do computation in parallel, sometimes synchronize their state, so you can learn your model faster and distribute computation. Okay, so the goal here is really to be faster. And in particular, there is something quite important, is that when you do distributed learning, because you have access to the full data set, the way you're going to distribute data across the different machines will be typically uniformly at random. So you're going to make this balanced, and you're also going to make this essentially the data look kind of similar in distribution across the different workers, because this is how you can parallelize more, right? If the data locally at each worker looks kind of similar, is distributed similarly, then you can probably do a lot more parallel computation and synchronize less often. So there are theoretical kind of results that show that, for instance. So here there is a major difference with federated learning, which is that in federated learning, the data is naturally distributed. You don't get to choose how the data is distributed, right? And in particular, it will often be heterogeneous. So by this, I mean that typically the size of the local data sets will be different across the different participants, maybe because you have more active smartphone users, or maybe you have bigger hospitals than others, whatever, right? So the data will not have the same size. But and more importantly, it will not be distributed in the same way. So in the statistical sense, right? So the distribution of data at each participant will be different because it will reflect the kind of the specific patterns at this entity, right? So different users will not generate the same kind of data because they don't type text in the same way, or they don't use applications in the same way, and so on. Again, different hospitals have different population of patients and so on. So the data will be heterogeneous. So here, I don't mean, so typically we're going to assume that the data will be in the same format, right? So there is a common kind of set of features that everybody agrees on to describe the data, but the distribution of these features will vary and be heterogeneous across participants. Another big difference, of course, is this aspect around privacy, and the data might be sensitive, right? In distributed learning, you have access to the entire data set anyway, right? So there is no need to enforce any kind of privacy constraint, which in federated learning can become very important when you learn on sensitive data like health data. And there are also a few other differences. For instance, the fact that in federated learning, the participants may be unreliable or sometimes unavailable. Okay, so if you think about doing federated learning on a set of smartphones, like deployed by Google, then, okay, people sometimes go in a tunnel, right? So they don't have network, and sometimes they go to bed and they put their smartphone in airplane mode and so on, right? And these things will also happen with possibly some time and space correlations. So it makes problems more complicated. And maybe a last problem that I'm going to mention is that participants in federated learning may be malicious. So as opposed to the cloud, kind of distributed learning in the cloud, where you can expect that machines are reliable and they will obey you, essentially. Again, if you think of federated learning as an open system, maybe on smartphone users, then you can expect that maybe some people join and don't follow the protocol, right? And will try to maybe act maliciously to make the training fail or to make the model learn something specific that is in their advantage or something like this, right? So there are kind of security issues specific to federated learning that you don't find in distributed learning. Okay, so that gives you a little bit of overview and explains why people have started kind of working on federated learning specifically and why, you know, there are these kind of distinct challenges from what people looked at before around distributed and parallel machine learning. Okay, there's a maybe good time to stop for maybe if there are questions now. So this was a little bit high level motivation and introduction. Now I will describe like a baseline algorithm for federated learning. So start introducing a few notations and stuff. So if there is any question.
I think you can go ahead.
Okay. Great. So let's look a little bit now at how this works, right? So let's try to introduce like a federated learning algorithm, which will kind of be representative of how these algorithms typically work. So I'm gonna introduce some notation. So we're gonna consider a set of K participants. So parties, participants, users, clients. Okay, I will use maybe different words, but and each of these parties, they hold local data, like we have said, right? So I'm gonna denote by DK the local data of party K. I'm gonna kind of typically assume a parametric machine learning setting. So typically we're gonna have a family of models with parameters, maybe the weights of a neural network or the weights of a linear model. And we're gonna want to train these parameters, right? Find the best parameters for the given data. And so I'm gonna denote by theta the model parameters. And typically the problems that I'm gonna focus on in the context of this presentation is formulating the learning problem or the training objective as an optimization problem, which is to find the parameters theta that minimize the overall prediction loss over all the data. Okay, so f is a function that measures how good the model parameter theta are at kind of making predictions for the data at the participant K. And we optimize the average over all participants. Okay, so of course you can do weighted average if you want. So maybe some users have more data than others, so you can maybe use a kind of a weighted average. For simplicity, I'll just consider a simple average here. And we're going to typically assume that the loss function f is differentiable in the parameters, so we can use gradient descent type of algorithms like we typically do in machine learning. So the advantage of this formulation, which is typically known as empirical risk minimization, is that it covers quite a broad class of machine learning problems. You can do linear regression, you can do logistic regression, you can do training neural networks and so on, that they all fit kind of this abstract formulation. So this is why it's convenient to work on that. Okay, so how do we solve this problem now in a federated learning setting where we are not allowed to share or to communicate the data? So I'm going to show kind of the classic baseline federated learning algorithm, which is called federated averaging. And so on the left, there is a kind of like a picture view of the algorithm, and on the right, in each step, I will highlight kind of the corresponding step in the pseudocode. Okay, so here we're going to assume for simplicity that there is a server. So the server is at the top, and the server doesn't have data. It's just here to kind of coordinate the process, right? So it will never receive any data, but it will communicate with the different participants. Here we have 4 participants, let's say hospitals with the data. Okay, so the first step is that everybody agrees on the type of model that will be trained, you know, the format of the data and so on. Let's say like here, small neural network, we're going to train a small neural network. And then this is going to be an iterative process. So there's going to be a notion of round. And then at each round, essentially each participant will compute locally an update to the current version of the model based on its local data. And so as you can see in the bottom client update algorithm, the standard way to do this is by kind of local stochastic gradient descent. So essentially each participant will do L steps of gradient descent locally on its own data. Okay, so L steps, there is a step size, whatever, the classic SGD or gradient descent type of algorithms, except that each of these participants do it in parallel. And then once they have done that, they will share their model updates with the server for aggregation. Okay, and so the server will aggregate these updates by taking the average of them. So this makes a new kind of global version of the model that is then sent back to the parties, and we iterate on that. They update their local copy of the model, and now they, again, train it locally a bit, and so on, until conversion. Okay, so it's quite simple in principle, right? So this gives you a little bit of a view of how this thing works. So of course, things can get a little bit more complicated, or analyzing the convergence of this algorithm can be tricky, in particular when data is very heterogeneous. You can have a problem if you do too many local updates. Then you might not converge to the solution of the problem, because everybody will just optimize on their own data too much, and then you might converge to something which is more like the average of the local optima rather than the global optima. So there are some careful things to set in terms of how many step size do I do. So if I do more local steps, then I communicate less often, right? I do more computation and communicate less, which is good because communication is typically costly. But if I do too many local updates, then I might not converge to the correct solution. So there are many extensions and improvements of this algorithm, some that work better with highly heterogeneous data, where you can use some kind of local correction terms to make sure that everybody is kind of going more or less in the right direction of the global optima. They are fully decentralized version. I'll come back to that a little bit later, where you remove the server and you only communicate, participants only communicate along the edges of a communication graph. You have, of course, kind of compression techniques. So sending these model parameters around might be costly if you train like a large neural network. So you can try to do some kind of compression to reduce the communication cost. There are questions also around fairness, which is making sure that maybe the model will be useful to everyone. You know, if there is a user that is very different from the average user, maybe learning a model in this way will not give a very useful model to that user. So there are things around personalization and making those more fair. So these are all things that I will not have time to talk about. And instead, we're going to focus on another thing, which is privacy. Okay, so what about privacy in this setting? So maybe intuitively, at least federated learning intuitively is good for privacy. This is one of the motivation, right? Because I don't communicate the data. So the server cannot see the data of the different participants, and one participant cannot see the data of other participants, right? So this is good, certainly better than sharing the data itself. But is it really better? This is not always clear, right? So because in the end, you do communicate information, which is kind of model updates trained on that data. And so it's possible in some cases that these model updates contain still a lot of information about individual data points, and that you could maybe reverse and do some attacks on. Okay, so this is exactly the problem, right? And we know, in fact, that this can happen, because this can happen already in the centralized setting. We know that machine learning models, they are susceptible to attacks on data privacy. Even an attacker that has only access to the final trained model can sometimes figure out information on the training data and individual data points in the training set. So for instance, the kind of things that one can do is membership inference attacks. So this is the setting where you have access to a trained model and you want to infer whether a known individual, so a known data point, was in the training set or not. Okay, so this can be a privacy issue because, I don't know, if this is a study on cancer, then being part of the data set means that the person has cancer. So this can be a privacy issue. And how this thing work, for instance, some attacks work by kind of exploiting the fact that models, typically large models like deep neural nets, overfit to some extent, even though they also work on test data. They generalize, but they are overconfident on training data, right? So there is a difference of distribution in the confidence that the model has in its predictions for data that was in the training set and data that was not in the training set. And you can exploit this to, predict whether some data point was in the training set or not, sometimes with quite good accuracy. You can go beyond that, and you can do also reconstruction attacks. So there has been quite some examples of those in the recent literature. I've worked a little bit on that also myself in the context of genomic data, where you can even, in some cases, reconstruct some of the points that were used to train the model. Okay, so kind of invert the model in a way. And I'm not going to spend time on attacks, but the point here is that these attacks already are real. They are not theoretical, right? So people have shown that you can successfully build such attacks already in the centralized setting where you only have access to the final model. And so from this perspective, federated learning is maybe not that good because it offers an additional attack surface, right? So if you are the server or you are one of the participants, you do not only observe the final model at the end when the federated training procedure has converged, but you also observe intermediate model updates. Okay, so in a way you observe more information, and so possibly this opens the way for even stronger attacks, and it is the case. So I've put a few references here that build kind of stronger attacks in federated learning scenario because they exploit that a participant in federated learning has access to more information than just the final model. Okay, so we have to fix this just like we have to fix that in general for machine learning. In fact, when we train models on sensitive data and we publish a model, we need to make sure that this cannot happen, right? And so to do this, okay, this seems kind of tricky, right? It's not very easy to control, and it's not very easy to define what it means for a model to be private. But luckily, there is a definition that has now become very standard in many fields, which was introduced like 15 years ago, but is now super popular in many fields, including machine learning, which is called differential privacy. So differential privacy is a formal way and robust way to define or to measure how much information about the input of an algorithm is leaked in its output. Okay, and so I'm going to give you here the kind of the intuition for differential privacy for people who don't know about it. So differential privacy is a property of an algorithm, and typically we're going to focus on randomized algorithms. So randomized algorithms here, they take as input some data points, okay, x1 through xn, and then they produce an output, which is a random variable, right? So there is some randomness in the algorithm such that essentially you can define a distribution. There is a notion of distribution of output, right? Or the output of an algorithm is a random variable that follows some distribution that of course depends on the input data, right? And so the idea of differential privacy is to say, okay, if I have two data sets which are the same, but where I replaced the data of one person by the data of another person, here the blue data point by the red data point, then of course the distributions of the output will be different because, right, my algorithm depends on the data. So if I change the data, I should change the distribution of output. But the distributions of the outputs in either case should not be too different. Okay, and so typically, so you want in a way that the distribution of A of D and the distribution of A of D prime is close for all possible data sets D and D prime that are so-called neighboring, so where they are equal up to changing 1 point. Okay, and so one way to define this notion of closeness can be this kind of bounded ratio. So this is, for instance, you say for any possible output, I want that the probability of observing this output in one case and in the other is similar, okay, in the sense that their ratio is not too large, right? So this yields kind of the classic, a little bit more formal here, definition of differential privacy, where we say that a randomized algorithm A is epsilon delta differentially private, so DP, if for all neighboring data sets, D and D prime, and all possible sets of outputs, the probability that the output that I observe is in the set S, if the data set was D, should be close to the same probability, but if the data set was D prime. Okay, and again, close means here there are two parameters that measure the strength of the privacy definition, epsilon and delta. The smaller they are, the stronger the privacy. So if you forget about delta and take it to 0, you see that epsilon bounds exactly this log ratio between the probabilities of any output. So this corresponds to kind of this figure that I showed before. And then delta gives you an additional slack, so it allows that for maybe sufficiently unlikely outputs, this ratio maybe can be larger. I'm not gonna maybe spend too much time on kind of giving more formal details on this definition, but you understand the idea, right? The idea is to say my algorithm is private if the distribution of outputs is indistinguishable when I change one point by another, meaning that someone who would be interested in knowing whether this data point was x2 or x2 prime will not be able to say much by observing the output of the algorithm, because distribution from which this output is sampled is closed. Okay, so I hope the intuition is clear. And so typically how to set these parameters to good values, so values that will provide strong privacy guarantees, but at the same time not destroy the utility of the algorithm, is always something that is subject to debate, but typically rule of thumb, right? So to get meaningful privacy guarantees, you should think of epsilon of the order of 1 or smaller, and delta very small, so typically much smaller than 1 over the size of the data set. All right, so I hope this definition makes sense. So maybe a key principle here, which is interesting to note, is that privacy is a property of the analysis, not of a particular output. So this is in contrast to k-anonymity, for instance. If you know about k-anonymity, this is a property of a particular output, in a way, a particular transformation of data. And this has turned out to be flawed in many cases, such definitions of privacy. Here, privacy is really a property of the algorithm itself. All right, and so these guys, they won the Gödel Prize for this, so the top prize in theoretical computer science. So they won the Gödel Prize for introducing this definition in 2017. All right, so let me give you a little bit of also reasons why this notion is now widely adopted. So essentially, it has very interesting properties that you want for privacy definition. It is immune to post-processing. So this means that if I compute any function on top of the output of a differentially private algorithm, then the composition of the two remains differentially private with the same parameters, right? So it means I can post-process the output of a differentially private algorithm without changing the guarantees. So this is very useful because it means if my algorithm is differentially private, I can publish the result, the output, and let people do whatever they want with. Differential privacy is robust to arbitrary auxiliary knowledge. So the idea here is that it's a relative guarantee, which holds even if the adversary knows almost everything. Let's say it knows all the data set except for one record, and it's not sure if it's x2 or x2 prime. Then the guarantee still holds because essentially it is about bounding the relative gain of information that any adversary will get by observing the output, right? So even if the adversary knows too much, maybe the adversary knows already a lot, and so maybe I'm screwed. It doesn't really matter if I published the result of my algorithm or not, but the adversary will not know much more in any case, right? So if it knew nothing or almost nothing, then it knows almost nothing plus epsilon, something like this, right? So in that way, the DP is robust to auxiliary knowledge. It cannot happen that everything was fine before, and now you publish the result of a differentially private algorithm, and all of a sudden it's a catastrophic leak. Okay. And then last property, which is very important, is DP is robust under composition. So this means that when you do multiple analysis on the same data, as long as each analysis, each algorithm satisfies differential privacy, then releasing all this information taken together will also satisfy differential privacy, but you will have a degradation in the parameters, right? So we know that this is unavoidable. If I reveal more and more results of computation on the same data, I will degrade the privacy guarantees. But the really good thing about differential privacy is that I can keep track of that. So I have essentially composition theorems which tell me how epsilon and delta will change as I reveal more things. Okay, and so I can have a notion of budget and say, you know, now I've revealed too much, you know, stop. I'm not going to allow any more computation on that data, something like that. So this will be very useful in designing algorithms because it will allow us to make kind of simple parts of algorithms differentially private and then get guarantees for complex algorithms by this composition rule. All right, last bit of information about this, and then this will leave me a bit of time to talk a little bit about how to apply these things to federated learning. So how do we enforce differential privacy in practice? You have very simple way to do that, which is called the Gaussian mechanism. So if what you want to compute is a function f that takes as input a data set and returns a p-dimensional vector, then you can use the Gaussian mechanism to make a private version of this computation by essentially adding Gaussian noise to f. Okay, so it's output perturbation. What you do is that you need to have a bound on the sensitivity of the function that you want to compute, which measures in L2 norm how much the output of the function can change if I change one data point. Okay, so if you think about the calculation of an average, this will be proportional to 1 over n, okay, because typically changing 1 point in an average change only of order 1 over n, the output. And then what you do is that you draw independent Gaussian noise in each entry of the output, which has a standard deviation that is proportional to the sensitivity and to the privacy parameters, epsilon and delta. The smaller they are, the more variance you're gonna need. And then you output the result of the true evaluation of the function, which is non-private, plus this Gaussian noise. Okay, it's very simple. You can show that the Gaussian mechanism, as defined above here, satisfies epsilon delta differential privacy for any function f. And of course, the noise, like I mentioned, is calibrated using the sensitivity of the function and the privacy budget. And you can see that this induces a clear privacy utility trade-off now, right? So what I will get as output is a randomized version of the computation, which in expectation will be equal to the true value, but will have some variance, right? And so this variance we can think of as the loss in utility due to privacy. If I want more privacy, I will have more variance in my result. Okay, but at least I understand the statistical property of the output, so I can do confidence intervals, and if the sensitivity is small enough, I have enough data, then I can still have very useful outputs from this, right? As soon as I pick epsilon and delta, not too small. All right. So let's try to think about how to apply this to federated learning, right? So remember that the idea with federated learning is that we were transmitting results of computations of data, updating models with gradient descent locally, and we want to use differential privacy to make sure that one cannot infer back some information about the data using these updates. So we will need to add noise essentially, right, to the model updates. So there are kind of different settings in differential privacy, which depend on a little bit of the trust model that you consider. So what has been considered like a lot in the literature is what's called central DP. This is corresponds to the centralized machine learning scenario, where you have a trusted curator that collects raw data. So you trust someone to collect the raw data and then run some algorithm and then reveal the result of the algorithm. Okay, so this is really centralized learning, where if this is a machine learning algorithm, it means you only reveal the final model that is trained. Okay, so this corresponds to the centralized scenario, which is not well suited to federated learning, right? Because precisely we don't want to centralize data. We don't want to trust someone, this trusted curator, with the data of everyone. And so there is another version which is called local differential privacy, which removes this trusted curator, and instead each participant locally randomizes its contribution. Whatever it shares with others, it applies locally a differential private mechanism on it. Okay. And so from the perspective of differential privacy, now the output of the mechanism over which the definition should be applied now consists of all the messages sent by all parties, right? So instead of observing only the final model that was trained, in the context of federated learning, I will observe all the messages, meaning all the model updates sent by everyone. Okay, so this is a much stronger model, local DP, because I remove this trusted curator and I add noise locally so that nobody else can figure out my data from the message that I sent. But as you can guess, this has a cost, right? So this means you will typically need to add much more noise because you will need to protect your own messages. It will not be blended anymore. and aggregated with the messages of others. And so you need to add a lot more noise. And so typically the utility cost is much larger. Typically when you have K participants, then the cost in utility measured in, L1 error or whatever, will be of the order of square root K larger, right? So if you have many, many participants, the cost in utility or how much noise you need to add increases very fast. So it's not very good, right? So this is the kind of cost to pay for this very conservative model where nobody trusts anyone and you just add noise locally to hide your own stuff. So this has motivated so you can apply local DP to federated learning, but often it leads to not very good utility, meaning that the models you get at the end, they are so random, there is so much noise in them that they don't work very well, unless you have maybe many users. So this has motivated the study of kind of more intermediate models, where you don't want to rely on a trusted curator or trusted party, but maybe you can do something a little bit better than just relying on your own randomization, on your own noise. Okay, and so this is exactly what I'm going to present. A little bit briefly to give you the main ideas, and maybe it's good for me to stop and also ask maybe how much time I have, if any.
10 more minutes, something like this?
Yeah. Okay, sounds good. I can try to make this maybe even slightly shorter to avoid going too much over time and leave a bit of time for questions. So I hope it was interesting and clear so far. So I think the main content of the talk, or at least the way I intended it, was also all these introducing all these notions and this context and these ideas. Okay, great. So let's now look a little bit in recent work, which includes some of my work on applying these things to federated learning in a way that achieves a better privacy utility trade-off than just using this local DP idea of everybody just adding noise independently of others. All right, so something that you can do to improve things is, okay, so first of all, how to apply kind of differential privacy to federated learning. Let's look at how it looks like. So if you remember this algorithm that I presented before, this federated learning algorithm, federated averaging algorithm with a server, you remember that the interaction between the participants was only needed to aggregate the local updates, right? This is the only thing that we were doing. We were sending these updates to the server so the server can aggregate them and send us back the aggregated version. And so what is nice about this observation is that if we know how to do differentially private aggregation, then we're done. We have a differentially private federated learning algorithm, right? Because we can make one aggregation at a given round differentially private, and then we do many rounds. So we do many aggregations of things computed on the same data. But for this, we can use the composition of differential privacy to account for the fact that we do this several times and get a privacy guarantee for the global algorithm, for the entire algorithm. Okay. So this is a useful observation because it allows us to work on a much kind of simpler problem or sub-problem, which is this problem of differentially private aggregation, right? So given a private value for each party, here for simplicity, I'm even going to assume it's a scalar value, not even a vector, but you can generalize this to vectors, of course. We want to accurately estimate the average of these values under a differential privacy constraint. Okay, so if we know how to do that, then we know how to do differentially private federated learning, essentially. Okay, so let's look at central differential privacy. In this case, if you trusted the server, let's say we trust the server for a second, then the server could just collect the raw updates, compute the average, and add Gaussian noise to it using the Gaussian mechanism, right? That would be nice. But in local DP, if I don't trust the server, then each party needs to add Gaussian noise to its own update before sharing it, and typically more Gaussian noise. Okay, which again we again find the problem that I mentioned before, that if we don't want to trust the server, then the utility cost will be a lot more. But maybe we can do something a little bit different now and say, add a little bit of a hypothesis over local DP. So local DP assumes that every message sent by everyone is observed by a potential attacker. And this is typically the case, right? If you assume, the server will observe all the messages. But maybe there are other tools, and in particular, there are tools from cryptography that one can use, in particular, the notion of secure channels. So you can do something better if you assume that pairs of participants can exchange encrypted messages, okay? In the sense that whatever I exchange with another participant directly, nobody else will observe except us, okay? And we know how to implement kind of secure communication channels, right? By encrypting communications and so on. So this can be achieved using standard basic crypto stuff like public keys and so on, right? So it's quite reasonable to assume that we can do that. And so now this relaxes a little bit this local model of differential privacy, and we can do much more useful stuff. So this is an example of what we can do. This is a paper with another permanent member of the team here and a PhD student, Cesar. You'll see that the protocol is super simple. So we called it GOPA. So it goes like this. So remember, we need to compute this average of private value, right? So what we're going to do is that each participant will generate some independent Gaussian noise, eta k. So this is exactly like you would do in the local differential privacy, right? Some noise that you don't tell anybody. But each participant will also select a random set of other participants, let's say M of them, uniformly at random. And for all these selected peers, they will go into an exchange, secure exchange, using these encrypted messages to essentially draw another Gaussian noise, which this time will be correlated. In particular, it will be pairwise canceling between the two users. Okay, so this big delta KL, this is the noise that will be added by party K, will be equal to the opposite of the noise that will be added by the party L. Okay. And now, after this has been done, each participant reveals the sum of its private value with all the pairwise noise and also the independent noise, and sends that to the server. Okay. So if you remove the pairwise canceling noise, this is exactly local DP, but now we have this noise that intuitively only the two users know about, right? And now if I sum kind of everything, so the server collects all these contributions and takes the average, then of course all the pairwise canceling noise cancels, because we sum everything, it sums to 0 by pair, right? And so we left only with the true average plus the average of the independent noise. Okay, so in a way, we don't pay any cost in utility for this pairwise canceling noise, but we can hope that it helps protect individual values, because unless everything is summed together, the server cannot figure out what is this value, right, in isolation. Okay, and so this intuition turns out to be correct, and we can prove this, right? So we can prove this against some adversary that is the coalition of the server with a potential also number of corrupted parties. Let's say a proportion 1 minus tau of the participants who collude with the server to figure out what is the private value of another user. And we have essentially a result that looks like this, stated here a little bit informally, which says if I take a logarithmic number of parties, if each participant exchanges with a logarithmic number of other users this pairwise noise, if I set the independent noise variance so as to satisfy, which is enough to satisfy privacy in the central model, so this is the noise that I would need if I assume that the server was trusted. Now, if the pairwise noise variance is large enough, and remember, we can make it large because it cancels at the end, so we don't care, then this protocol satisfies essentially the same privacy guarantees as in the central DP case. Okay, so essentially this is the same utility as if I assume that the server was trusted. And there is an overhead, which is we need to do some pairwise communication, but only a logarithmic number of messages per participant, right? So it scales nicely to even large number of participants. Okay, so this is a little bit the idea of this protocol, and in practice it works very well. Maybe I was going to skip these figures, but the idea here is that, yes, if we do that, we learn the models that are much better on the right in terms of accuracy than local DP, because local DP needs to add so much noise. So it's crap, but if I compare what I get in blue with my protocol compared to assuming that the server is trusted, then I get almost the same thing. Okay. Good. So this is one thing you can do when there is a server and you assume that you have access to this kind of encrypted message technology, right? Let me spend 1 minute to give you just an overview of the fact that you can also do such things in fully decentralized cases. So this is, again, the setups where you don't have a server, but instead the participants communicate only with a subset of other users as defined by a communication graph, right? So party K here has some neighbors in the graph and only exchanges messages with those guys. Okay, and so the idea is that now there is no global aggregation. The nodes will only do some kind of local aggregation steps. So we cannot use the previous technique. But now each participant only has a limited view of what's going on in the algorithm. We'll only observe a subset of the message. And so we can show, in fact, that in this case, also leveraging the fact that everyone has only a limited view, there is no more a server that observes everything, we can also prove much stronger privacy guarantees, okay, and add noise which is in the same order as in the central model. And so I will skip all these details. So we define some kind of relaxation of differential privacy that accounts for this limited view. And then we do some algorithms like random walk. So we update the model sequentially in a graph and things like this. And the message being similar to the previous part, even if I don't have a server and I do this fully decentralized algorithms, I can also harness this kind of limited view and end up with recovering essentially the privacy utility trade-off of trusted curator. All right, just skipping this, I can come back to it maybe if there are any questions. And I just have maybe a concluding slide with a few take-home messages. So maybe to summarize a bit what I talked about. So federated learning allows to train machine learning models from decentralized data sets. But unfortunately, we know that not sharing data directly is not enough to ensure privacy. And so to really have strong guarantees, we need to go kind of with these formal notions of formal notion of privacy, like differential privacy. We have seen that differential privacy is nice, but it induces this privacy utility trade-off. And this trade-off can be quite bad if you assume that nobody trusts anyone and everybody observes everything, which is the local model. But we can do better under some assumptions. So in federated learning with a server, we can kind of use these encrypted messages to achieve the same utility as in the central model without blowing up the computation or the communication cost too much. And in fully decentralized federated learning, we show that we can naturally amplify privacy guarantees. And again, we cover this same privacy utility trade-off. And people typically use these fully decentralized algorithms for their scalability to a very large number of participants. And so what we show is that they are also good for privacy, in a very formal way. That's it. Thanks a lot. And sorry for going a little bit over time.
Merci. I'm sure there will be questions about federated learning on the one hand and privacy on the other. So who starts? Okay.
Thank you for the talk. And has it been tried to use an unstable learning classifiers with each local fully learned classifiers?
Yeah, that's a good question. So maybe I can do two separate answers. So there are techniques to train a private privacy preserving model that satisfies differential privacy in the centralized setting, which is based on this idea of splitting the data and having kind of different teachers or different learning algorithms that train on separate data and then do some kind of private voting, majority voting. So based on ensemble learning, so this is called PATE, and this is quite a popular algorithm for enforcing differential privacy in the centralized case. And yes, so you can also do things like this in the federated learning setting, with or without privacy, right? The problem with voting, at least if you do it naively in federated learning, is because the data is heterogeneous. Right, if you assume that data is distributed uniformly, then this will work well, right? But if like it is the case in many problems, the local data sets are not are heterogeneous, they are not distributed in the same way, then kind of doing this uniform voting might give you not what you want, right? Might kind of bias the decisions towards maybe some types of inputs or some users. So there is kind of care to be taken in terms of whether doing this uniform voting makes sense.
Okay, thank you.
So this comment is related to the Pate scheme. Do you know the Pate scheme, which has been invented by Nicolas Paperno?
Yes, this is what I was referring to. Yes.
Yeah. Okay.
Can you tell us a little bit about the robustness of the things you learn when some participants are malicious?
All right. Yes, this is a very good question. So this is a tough problem which can be tackled in various ways. So there are at least two that I'm aware of. I've worked also a little bit on that. So the first way you can try to tackle this is by kind of robust aggregation. So indeed, in kind of standard federated learning, like in this federated averaging algorithm, we do averages of contributions. And so if there is even just a single malicious party which sends like a very large update or a very biased update in some direction, then it's very easy to influence the average, right? Because the average is not really robust to kind of outliers or things like that. So it's possible to use ideas from robust statistics to do kind of more robust aggregation techniques. Things typically, I mean, you can think about the median, but the median is not always kind of so easy to manipulate in high dimensions. But things like trimmed mean or all sorts of kind of robust estimation techniques that you can use instead, which will kind of naturally be insensitive or not too sensitive to having like a certain proportion of malicious participants in the learning. Okay, of course, if you have too many malicious participants, you can probably do nothing, right? But okay, so you can do something like this. Again, things get a bit more complicated if data is very heterogeneous, because then it becomes very difficult to tell apart someone who is malicious and sending fake updates from someone who is just different from the typical users, and the updates of that person will look different from the others, but maybe it's normal just because this user has different data, right? So if you allow data to be potentially very heterogeneous across users, it becomes a bit difficult to use these techniques. Then the second thing you can do is rely on crypto. So all the kind of techniques that allow to do kind of verifiable computing. And so in fact, we worked a little bit on this for the first protocol that I mentioned, the one based on encrypted messages. If I can get the slide. Yes, so I had just one item here that I didn't discuss. Okay, no, sorry, that's not this one. Here, yes. So there are ways to use tools from the crypto community, things like commitments, cryptographic commitments, and zero knowledge proofs, and these kind of techniques to kind of on top of an existing protocol, having some additional computation and publications of encrypted quantities that can be verified after the fact and allow to potentially detect if someone deviated from the kind of computation that they were supposed to do. For instance, instead of adding Gaussian noise, they choose a particular value from the noise that was not random and that they choose on purpose. Then you can kind of detect when that happens. And so for this GOPA protocol, the one that I introduced here, this simple one with independent Gaussian noise and pairwise Gaussian noise, we actually have derived a version where we can provide correctness guarantees against malicious parties, meaning that with high probability, if someone cheats, so someone lies, didn't draw the noise correctly or lies about the noise or things like this, then you can detect it. Something you cannot detect is, bad input data. So, I mean, it's impossible to force people not to lie about their data. So you cannot really prevent the fact of malicious parties giving you wrong inputs. But if you consider that you're going to use these inputs several times, then you can still use commitments to make sure that before any computation, everyone commits to its value in a way that can be verified later, so that we can make sure that always the same value will be used consistently in all subsequent computations, which can reduce a bit maybe the incentive of lying or being malicious. Okay, so these two things can be used, and I think there is still quite a lot of work to be done on this more crypto-related side, in fact.
So how much do you think that Byzantine fusion at the aggregator will violate the privacy itself?
I'm sorry, can you say that again? By applying what?
I think the microphone is here.
Oh, okay. So how much do you think that the Byzantine or robust aggregation at the server side will violate the privacy itself?
Oh, right. So this is a good question. So yes, so here, I mean, the protocol I presented are for kind of averaging, right? And indeed, the privacy guarantee is built on the fact that you do an average, you don't do like a robust aggregation or something like this. So this is a very good question. So in general, I mean, there is a lot of interaction, in fact, between the people working on differential privacy and robust statistics. Because if you remember about this concept of sensitivity, so sensitivity is how much like a function value can change if you change one input data point. And you calibrate the noise to this in differential privacy. So the more sensitive, the more noise you need to add. Robust statistics are typically, I mean, they are designed to have low sensitivity, right? They are designed so that their value doesn't get influenced too much by just a single point. So generally, those two things go quite well together. Then, of course, analyzing precisely the privacy guarantees is for robust statistics is typically not so easy. But there are many papers investigating this, and in general, I mean, generally speaking, using robust computation or robust statistics tends to help for differential privacy because it reduces the sensitivity kind of by design, right?
Thank you.
I have maybe a naive concern about federated learning. I've seen recently a video from Lei Nguyen Hong, who runs the YouTube channel Science for All, and he claims that with people from the EPFL Lausanne, they have been working on the security or more widely privacy with federated learning, and their claim is that these models are maybe dangerous by design, and they say that according to their knowledge on what they saw on the reviews that they did, that somehow it is impossible to produce a safe and totally secured model, even if it is learned through federated learning, because they aim to produce a model that has the same behavior as if it was learned centrally. So their claim is that even using cryptography, it is hard or maybe impossible to build something that is secure today. I'm kind of new to this domain, so this is probably naive, but have you heard about this, and what do you think about this information?
Yeah, okay, thanks for asking. It's also nice to hear that people listen to Lei. So I think he's doing very interesting work in general. So I'm not too sure I see precisely what you're talking about. So I'm aware, for instance, of a recent work which is not specifically on federated learning, but more on like very large models, like these foundational models that people use in for language modeling and so on, like GPT-3 and so on. So where they do this kind of is it what you are talking about, or?
Yeah, that's it. Yeah, exactly.
Okay. So I think their claims there is not so much about federated learning, but about the ability of learning such huge models while having some privacy and security guarantees. And to some extent, yes, this is, at least as far as privacy is concerned, this is very difficult and potentially impossible because, so I didn't talk about this explicitly here, but there is some kind of curse of dimensionality in differential privacy, which is here. For example, with the Gaussian mechanism, I add the noise to each dimension, right? And so if I look at the error now that I make on f of d, this error will scale polynomially with p, the dimension of the output. So the higher dimensional, kind of the larger is the error to get a fixed privacy guarantee. And so if I apply this to like these trillion parameter models, this gets super bad, right? And so there is a trade-off also in differentially private computation and privacy-preserving machine learning with dimensions. So there are things where we are not able to get useful utility. So it's a bit this impossibility that you're referring to, right? The fact that getting at the same time a useful model and a private model might be impossible, because if you want things to be private, the model is so high dimensional that you need to add a lot of noise. And if you don't add a lot of noise, then the model is so high dimensional that it can memorize a lot of things. And in fact, it's a problem for privacy, right? And so there is a trade-off. And so I think in that paper, they also kind of call for, a stop in kind of increasing the size of models for these very big models and stuff, which is consistent with differential privacy, right? Because differential privacy will tell you, if you want privacy and good utility, you might be better off using a smaller model on which you can actually enforce privacy without this huge cost that depends on dimension. And so we see that in practice a lot. So for instance, what happens when people try to train such big language models with differential privacy is that it's very difficult to achieve this with good privacy guarantees if you train the entire model on private data. But you can do things that work much better if you consider that maybe the big model is trained on public data, and maybe for public data, let's say you don't care about privacy guarantees. This might not be as simple, because it's not because you can find data over the internet that it's, this can cause problems too. But assume you have a large enough corpus that is public, so there is no sensitive information in it. But then you want to use your model on sensitive data, let's say in the healthcare domain. So you have a private data set that you can use to fine-tune this model, right? So in this case, you don't enforce privacy for the public data, but you want to enforce privacy for this fine-tuning phase. And now you can achieve things that work fairly good in this case, because typically what you will do is not train the entire model, not fine-tune all the parameters, but you can, kind of just adapt a few layers, or, something which is much lower dimensional, which is enough for the model to adapt well to this private data. But you touch only a rather small number of parameters, and thus you can have like a good balance between the two.
So doing so, you're less prone to regenerate private data.
Exactly. So in this case, probably the model will have memorized the public data, but if you don't care about that because it's public, it's fine. And then in this fine-tuning phase, you can control much more effectively the privacy utility trade-off for the data that is actually private. So because you work on a smaller dimensional object.
Okay, thanks.
Can you go back to your COPA scheme where you add the delta KL?
This one?
Yes. So what is the amplitude of the delta noises?
Oh yeah. So in the interest of clarity, I skipped this. So I think I have actually the detailed version in some backup slide. Maybe do I? I do. Yeah. So it looks like this, right? So you have different parameters for the noise variance of the pairwise cancelling noise, so the sigma squared delta, and for the independent noise, the sigma squared eta. And so these are parameters, right? So you need to set them in a good way if you want in the end to have good privacy, kind of optimal privacy utility trade-off. And so in our paper, we know how to set that. So we have explicit values for setting this. So the variance of the independent noise, essentially you will choose to be the same as you would use for the computing an average in the central model. So exactly like in the Gaussian mechanism slide, if you have a bound on the values of the input, here they are between 0 and 1, so you know the sensitivity and you know how to scale this noise. And then this pairwise noise needs to be large enough, and we give kind of sufficient, so here it's big O notation, but we have actually practical values. So this is what I wrote on this slide. So we have practical values for these parameters that you can use and this guarantees that you have, the privacy that is claimed in this result. So our results are explicit in the sense that we provide sufficient values for these variants to get the results that we want. They might be not completely tight. So in fact, they are not. So because the analysis is not perfect, so it tells you to add a bit more noise than what you actually need, but it's not too far, and so it's still practical. And of course, the pairwise variance, you don't care too much. So the only thing that you pay for adding variance too large for the pairwise terms is kind of blowing up the communication, because you blow up the representation size of numbers, because numbers become big. But in the end, things cancel. So if you don't care too much about increasing the communication, I mean, picking the pairwise noise too large is not really a problem, because at the end, things will cancel.
But if it is too large, then the server can maybe guess that the K is paired with L.
The server can guess what, sorry?
That K, party K, is paired with party L.
Oh, okay, so maybe I should make this more clear. I guess I haven't. So this is known by the server. So we assume that the graph of who exchanged noise with who, this is actually, we consider this known by the server. Okay. This is public information. It doesn't have to be hidden. What needs to be hidden is just the values of these things, right? The idea is that the server knows that, let's say, I communicated with this M other folks. Some of these folks might have colluded with the server, so he knows maybe some of the values, but then there are all the other values that the server doesn't know. And these are enough to do the job, basically.
Okay.
Okay. Merci beaucoup Aurélien pour cet exposé extrêmement riche.
Thanks a lot. Désolé d'avoir d'avoir dû aller un petit peu vite à la fin, mais peut-être que c'est intéressant d'avoir quand même pas mal de temps sur la première partie. C'est plus introductif, hein, je sais pas, mais peut-être je me suis trompé, mais je me suis dit que c'était peut-être mieux.
Non, c'était très bien.
C'était très bien.
Bon, tant mieux. Merci pour l'invitation.
Merci beaucoup.
Merci.
Allez, bonne journée. Au revoir Aurélien.
Merci, à vous aussi. Au revoir. Merci.
Okay.